So let's return to an example we looked at early in the course and use symbolic inversion methods on it. So the example I have in mind is the one where we look at these sums. Let me show you what they look like. Like this. So these are the kinds of sums we are, to the, like so. So we have powers, we sum r from 1 to n and have powers of r. And then we get these nice closed expressions in n alone and find that they are not only polynomials of degree 1 more than the power of m, but also that the coefficients are very systematic. For instance, in the beginning, it's easy to see that we get 1 over 2, 1 over 3, 1 over 4, and so on. But when we look at the other end of these expressions, we get something which is much more complicated, where we have some strange constants coming up, and this requires some sort of explanation that we try to get from just looking at the data, and that's not so easy. So let's try to use a symbolic inversion on the last coefficients in these sums of powers. So it turns out that if you look carefully, you can explain all the other things that go on alone with these values here. So that's really the most important part. We see when we pull out these 21 numbers that we have alternately 0 and non-zero, and some signs that tend to be systematic as well, except in the very beginning where we have some different behavior at the second entry, which corresponds to the value 1 here. So what happens here is that we generate a sequence of fractions, and that sequence of fractions we would like to understand. And the first thing that comes to mind is to take this data and feed it back into Mabel using guessgf. And surprisingly, it doesn't work. I mean, I've tried all kinds of things. I tried to give it back to Mabel in various ways, but Mabel is not able to find the generating function describing these numbers, even though there is one, which is quite nice. So I think that's a weakness of the way that things are set up in the gfun package. But I just cannot make it work. So that, I mean, I could show you various things that I've tried, but nothing would work. So let's skip that. So instead, let's try to feed it to the OEIS. Well, the problem is then that, of course, the online encyclopedia of integer sequences does not contain these fractions that I'm encountering here. So we have to come up with some way of replacing these fractions with integers. And there's all kinds of things that we can try, and it turns out that for this particular problem, since it's such a prominent problem, they will all work. The most natural thing, I think, the first thing I would usually try is to try to factorize these numbers and see if I can find a pattern in the denominators so that I can cancel them out and get integers this way. And indeed, that seems to work very well. When you look at the denominators, they are factorized. Of course, there might be some numbers that are divided out both in the numerator and the denominator. We can't really know that. But when you look at what's left in the denominator, this is certainly of the nature products of small primes. So this makes me think of the factorial function, and I try various ways of multiplying on I factorial. So what works here is that I've put I factorial, but actually, and this will give me integers, actually it probably would have been a little bit more natural to look at I minus 1 factorial, because the entry number 1 in my list corresponds to the power 0 in the function over here. So actually the entry at Li corresponds to the power I minus 1. I've tried that, but it didn't give me an integer, as you can see, so I had to go up to I. And then I can take this data and I can try to feed it into the online encyclopedia. I could also do another thing, which is perhaps a little bit naive. I could just simply say, well, if I have a fraction, then let's look at the numerator, let's look at the denominators, and see if they give me some hits in the online encyclopedia. So I can go to the online encyclopedia and feed this in. So I will take my data that I just generated before, this data here, and feed it in here. And I get a hit. So I get that this is n factorial times the n minus first Bernoulli number. So in a sense, this is a very promising hit in the sense that this is some person who had looked at some fractions and multiplied on by n factorial to get them to be integers in just the same way that I did. So actually, that's because we were looking at exactly the same sequence of fractions. And of course, you can read this, and there's various. Now you have a name. You can go, even though Bernoulli is a very common name in mathematics, but there's various kinds of references you can look into. There's, for instance, there's an Eric Weinstein's World of Mathematics description of the Bernoulli numbers that will tell you all you need to know about what these numbers are. But of course, I could also try with my numerators. The reason why I'm saying this is naive is that the numerators are, of course, that's a somewhat sensitive thing to work with, because the numerators, that's what remains in that fraction after you cancel out all the common divisors in the numerator and denominator. So it might very well be that the information in these numerators is really destroyed by the fact that sometimes you divide it through by 2 and sometimes you don't, depending on whether 2 divides the denominator or not. But here it's actually going to work. And again, it's the Bernoulli numbers. And if I do the same with this was the denominator, I could do the same with the numerators. That would also work. So the Bernoulli numbers that's a very important thing. And even though it's so important, I don't know of a place that I'm certain that you've seen it in your mathematical education here if it was here in Copenhagen. So let me just say a few words about what they are. So they were discovered by Jacob Bernoulli. This is a big sort of family of mathematicians, Swiss mathematics family, who was exactly trying to solve the problem that we've looked at with the sums of the powers, coming up with closed forms for them. And so he realized this pattern that describes the Bernoulli numbers, in fact, at exactly the same time as a Japanese mathematician did the same. So it's sort of an interesting coincidence that this is something that was discovered more or less at the same time in two sort of not connected scientific environments. The best way of describing the Bernoulli numbers is via this kind of recursive formula, which is perhaps a little bit hard to parse. So let me point out that it's a different formula that I have in the book. In the book, I have put here a delta function, which is, so it's a 1 if n is 0 and 0 otherwise. And that corresponds to the choice of having not plus a half, but minus a half here. So actually, there's many good reasons to prefer minus a half to plus a half here, but plus a half is what comes up when you do this general form. So this is what I went with. And then if you want to stick with plus a half, this is the right formula to use. So what does it say? Well, maybe it's a little bit easier to understand if we write it out, because it's a sort of an infinite sequence of equations, and you can use them to compute the next Bernoulli number. Right? So it's sort of it's recursive, and it's also implicit in the sense that you need to solve an equation in order to figure out what the next Bernoulli number is. But starting from the beginning with n equals 0, it says that b0 is 1, which we've already found. Then the next one is that b0 plus 2 times b1 is 2. So since I now know that b0 is 1, the equation becomes 2b1 oops, 2b1 is 1, so b1 has to be a half, and that's also what we had up here. Actually, maybe in order to make this a little bit more readable, let me repeat this down here. That is because I have now done this again. I've defined m to be something, and I've defined n to be something. I'm teaching all kinds of things that you shouldn't do. There it was. So we solve this equation and we get that b1 is a half. And then I keep on going. So if now I know b0 is 1, I know that b1 is a half. So this means that 1 plus 1.5 plus something is 3. So that means that what I have left here has to be a half. So that makes b2 equals a sixth. And then you can keep on going with binomial coefficients this way, and you compute these numbers. So, this is what you can do. You can simply compute these numbers using the recursive formula. This is something you can do very quickly to very large indices, and then you can use a formula that's based directly on these Bernoulli numbers and some binomial coefficients to compute the correct closed forms for the sums of powers, or to plug in values in them. So this is such an important thing. It comes up in all kinds of mathematics, and actually it also has the distinction of being the goal of the first computer program ever written, if you accept Charles Babbage's machine, which was entirely mechanical and actually was never built as a computer. Then the first computer program was written by Ada Lovelace to compute exactly the Bernoulli numbers on that machine. So that machine never came into existence, but the program was made and published, and it sort of uses these recursive definitions to compute the Bernoulli numbers. So even though you may not have heard about them before, these come up in lots of situations, and so you sort of need to know about them if you're doing experimental mathematics. I've mentioned this before, but I always go by this number here, which happens to be the postal code of Herlev, close to Copenhagen. So if you see that, it's definitely the Bernoulli numbers.